Hello and welcome to Friday's edition of Cracking the Cryptic. Now we've already done some extraordinary puzzles this week, but today we have another Sudoku that boasts a perfect rating on Logic Masters Germany, literally 100%. It's called Roses and it's by Pulverizing Pancake. And I'll read you the rules in a moment, but the first thing I need to do today is to read out the names of the correct solvers that we've had to our Hitchhiker's Guide to the Galaxy Sudoku hunt over on Patreon. I started to read them yesterday, but there were simply too many to get through, and there are still too many to get through, so I'm just going to read a few of them today, and then we'll keep going during the rest of the weekend. So, well done to Cricket and Zizenks, Nico Tishterman, I hope I'm saying that correctly, Peter Sputh, I hope I'm saying that correctly, Dave DeLong, Matt Boyack, Declan Hoare, Alice, Andy Mitz, Sarab Das, Rad Halim, Bryson Kinnan, Mike Daniels, Kevin Quitano, Robert Madison, John Chang, Yannick Boonstra, Jan Lim, David Hans, Trevor, Hilarious Happy Star Tao, Kim Geiger, Matthew Noteboom, Paul Tarjan, Mudit Mittal, Andrew Weimholt, Billy Fishmall, Mike Smith, Ian Randall, Jerome Dooman, Matthew Brockwell, Ryan Perry, Hanika Huisinkveld, probably, Sohil Bagat, Frank Gevertz, Guillermo Heras Prieto, and Mark Wiseman. Wiseman, that's a very good name for somebody who solves one of our Sudoku hunts. Yeah, so if you wonder what this is all about, well, this is the Hitchhiker's Guide Sudoku hunt. It's available on Patreon. Do check it out. Lots of people enjoying it mightily. Apart from that, let's read the rules of Pulverizing Pancakes puzzle. That pseudonym always makes me laugh. Right, normal Sudoku rules apply. In cages, digits sum to the small clue in the top left corner of the cage, and digits cannot repeat within a cage. So normal killer Sudoku rules. Digits along arrows sum to the digit in that arrow's circle. Okay, we've got 3 arrows in the grid, so basically add those 3 up and put the result in that cell. And clues outside the grid give the sum of the digits along the indicated diagonal. Digits may repeat along such a diagonal if allowed by other rules. So these squares here along this diagonal have to sum to 35, and we can repeat digits providing we don't break the rules of Sudoku or Killer Sudoku or Arrow Sudoku or anything else that's going on. So, don't know why it's called Roses. Why is it called Roses? Oh, maybe it's the... Yeah, maybe. Maybe these cages sort of... That does look like a bit like a rose. Even me, with my lack of artistic merit, can appreciate, well, sort of. Maybe these are 2 roses in the grid, and that's why. You guys will tell me. Anyway, do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. Now, I'm probably about to be completely proved wrong here, but this does scream Ard van der Wetering to me. And Ard van der Wetering's sort of set theory trick, which if you've not seen before, well, you're going to see it now, because this must be relevant, surely. Let me just, hang on, just give me a second. I'm just going to see if there's anything truly obvious that I should be... I mean, I can see that 15 cage actually has got to be 1, 2, 3, 4 and 5. No, but I can't see what else that might mean. I'm going to do it. I'm going to go with it. I think this might be important. So, Ard's trick is to say that these 25 cells there are identical. Whatever the digits are in these 25 cells, they are identical to the green cells plus 1 set of the digits 1 to 9. So you can see there are 16 green cells. If we added a complete set of the digits 1 to 9 to green, we would get the exact composition of purple. And the way to prove that to yourself, if you want to, is to, let's restart, is to just do some very simple set theory on rows 1 to 5 of the grid. So I think we'd all agree that these 5 rows of the Sudoku, 5 complete rows, would have to contain the digits 1 to 9 5 times, because it's 5 complete rows. Now, if we ask the same question about the last 4 columns of the grid, what would we say these had to contain? Well, we'd say those squares have got to contain 4 sets of the digits 1 to 9. So all we do then is to note that, okay, so purple, at this point we can say purple equals blue plus 1 set of the digits 1 to 9. So we've got 5 complete sets in purple and 4 complete sets in blue. But so if we imagine that equation, what that looks like, so on this side of the equation, we've written out 5 sets of the digits 1 to 9, and on this side we've written out 4 sets of the digits 1 to 9, and then separately we've got plus this extra set of digits 1 to 9. Then clearly we can just cancel anything that appears on both sides of the equation, which is every cell that has 2 colours in it. So let's just get rid of whatever those digits are. They don't affect anything. And we're just left with purple equals blue plus 1 set of the digits 1 to 9. Now, the reason I think this might be relevant here is because I've seen this pattern before, but we've got so many cages here that almost completely fill the purples, and you can see the blue cages almost completely fill, or the blue cages almost completely fill the blue colours. So we're going to get a relationship between the uncaged cells. You can see there are 5 uncaged purple cells and this little cell down here, if we use the power of maths. So that's probably what we're going to have to do, I think. So we've got 15 plus 27, that's 42, 69, 78, 84. Right, we're going to have to remember this. 84 in the purples. And in the blue cages, we've got, is there a simple way of doing this? There probably is, I just can't see what it is. 42, 57, 80. Right. So we know that we've got to add to the 80 one complete set of the digits 1 to 9, don't we? So that gives us 125. So we therefore know that 41, the difference between these purple squares and this is 41, which is huge. That is a huge difference. Right, so let's think about this, because let's try and make this square as small as we can. Let's make this 1. So now, if this was 1, these squares would have to add up to 42 in order to make sure that sort of the maths works. Now 42, we could do 8, 9, 8, 9. That would be 34. This would still be an 8. Right, that's nearly beautiful. It's nearly beautiful. We've got 1 degree of freedom. Bobbins. I've probably done the maths wrong. That's what I'm thinking. Oh dear, this could be very embarrassing. Well, okay. If I've done the maths right, then each of these squares, if we made those 8, these 8, 9, these 8, 9, this would have had to be an 8. But obviously I could make this a 9, and then I could reduce any of these 4 squares to a 7, 9 pair, and that would still be possible, I think. Or this could be a 2, and then this would max out again with a 9 here and 7, 8, 7, 8. So this is not quite good enough. 29 here, 1 second. So no, okay, that's not going to help us. So we're going to have to maybe we can do something with the arrows actually. If that's a 1, some very interesting things happen. These arrows are strangely symmetrical, aren't they? If this is a 1, yeah, we get 2, 3, 4 triples there, because you can't make, once you've got a 3-cell arrow that can't have a 1 on it, it must be 2, 3, 4 in order to make sure the arrow circle is a 9, because it can't be 10, for example. So 9 would get forced into there. 2s, 3s, 4s get forced into those squares. Not quite. Ah, no, it is good. This is good. Well, it's good in the sense it's not good. It doesn't work. Right. So if this is a 1, the puzzle is broken because 9 is forced into the 15 cage where it's got to have 2 other cells in it that add up to 6 that are not 1, 5. So we need to put 2 and 4 in this 15 cage, but you can't. Because look, the only cell in the 15 cage that could possibly contain a 2, 3 or a 4 is this one. And I need to put 2 cells that have 2, 3 and 4 in. You can see, well, yeah, the simpler way of looking at it is that neither of these squares can be 2, 3 or 4. So you can't make the 15 cage work given where the 9s would be. Good. Well, that is quite complicated, but very pretty indeed. This is huge as well, because now this square cannot be 1, so it must be 2. Now these 5 squares have to add up to 43. How on earth can we do that? Well, there's only one way. These squares will all have to be 8s and 9s, and that will have to be a 9. And that means we've got 34 plus 9 is 43. Oh, yeah, we've got 43, but I'm just noticing this 9 is actually in this cage, so that gets fixed. Which fixes that, and fixes that, and there we go. So we're off to the races. Now, oh, right, now the 29 diagonal has already got 27 on it in 3 cells, so we must fill that with double 1. Now you can't put 1 in this 9 cage anymore because of these 1s. They see every cell. So that's got to be 2, 3, 4. Now hang on, where do we put, yeah, look at this, the 15 cage, which we know must contain 1, 2, 3, 4 and 5, the 1 in it can only go there now. So these squares are 2, 3, 4 and 5, and those 2 squares are 6 and 7. You can't put 1 in either cell of the 6 cage now, so that's got to be 2, 4. And if we look at the 2, 3, 4 triple in box 5 now, one of those 2 squares must be a 3. Therefore, this square can't be a 3. And I'm just wondering about the 27 cage. Yeah, here we go. This 27 cage can't contain a 9, and it has a 1 in it. So the other 4 digits must be 8, 7, 6 and 5, which do add to 26. So, oh, yeah, and okay, and the 8 in this 27 cage, which must be in it, can only go there. So these are 5, 6 and 7. And this, I think this odd trick has completely broken this puzzle open. Oh, this is 27 as well. And this also can't contain a 9. So that needs an 8 in it. And that 8 can go there, I think. So these squares have got to be 5, 6 and 7. And we've actually managed to now pencil mark the entirety of this 5 by 5 box. Now this, well, this and this by symmetry, now we can't put a 2 on the arrow. The minimum we could put on this arrow would be 1, 3 and 4, which add to 8. So this square is an 8 or a 9. This square is an 8 or a 9. Yes, and both of these arrows have to have a 1 on them because they can't have a 2 on them. And the 1 here must go there. And the 1 here must go there. Yes, and I'm doing quite well today. Now, in column 2, what's this square? The answer is it's got to be a relatively low digit. It could be as much as 5, but it definitely can't be 6 because if this is 6, the minimum value of this square is 3, and this arrow would add to 10. So this has got to be 2, 3, 4 or 5, and look what's happened there. That's a quadruple on 2, 3, 4 and 5, so that's not 5. Now we've got a 6-7 pair in this 27 gauge, so that's become a 5. That's no longer a 5, so one of these is a 5, so this is no longer a 5. That's not a 2 either, so this is 3 or 4. So let's think about what this square can be now. If this is a 3 and a 1 adding up to 4, this can be a maximum of 5. Okay, 5, 4 or 3 into this square. And one of these two squares must be a 3 because we can't make them a 4-5 pair, because that will make 10 once we add the 1 in. And I've got a 13 diagonal here now as well. Does that have to have a 2 on it maybe? 3. We can only have one of 4 and 5. Oh no, it doesn't. Okay, sorry, I thought this 13 diagonal might be the next place we needed to look. Oh, okay, 8s and 9s. Let's do Sudoku in this Sudoku puzzle. That square's got to be an 8 or a 9. Because look, there's 8s and 9s, 8s and 9s. So the 8s and 9s have to be in these 3 squares of box 7. And the same is true, okay, using the symmetry in row 2. We can never have 8 and 9 on this arrow. In fact, I should check this arrow because presumably it works a bit like this one. Oh no, it's not quite as... Oh, it's because of the shape of the 15 cage, isn't it? This 15 cage in this direction is a little bit more powerful than it is in this direction. So although this square is subject to the same restriction, which is that this has to be a 2, 3, 4 or 5, it's not a 2, that doesn't seem to create a quadruple in the row. Well, bobbins. Okay, okay, so this square here is 3, 4 or 5 as well. So there must be a 3 in one of those. Now maybe we can lock 3 into somewhere useful in box 9. No, we can't. Oh, 1 as well. No, I mean, I can see simple things like you can't put the 1 and the 3 in the 23 cage. But knowing that there's a 1 and or a 3 in one of those two positions does not seem to be... Well, it's not terribly revelatory, is it? What on earth am I meant to do now, then? I've got this square. Yes, this square is a 6 or a 7. Just to complete this column, we've got the quadruple, we've got the 8-9 pair, and we've got a 1. So we must be left with a 6-7 pair. So these squares are 2s, 3s, and 4s, which means one of these two squares is definitely a 3. Okay, that doesn't seem to do. I've not used this 35 either. At the moment I've got 16 on it, so I need another 19. Those two have a minimum value of 11, so I need a maximum of 8 in those. It's not enough. There's not enough restriction. This 8 arrow, I've not looked at this. No, that doesn't look great, does it? I think all 3 options for 8 in 2 cells are still available. Oh dear, I'm missing something here. What is it? Maybe I can do better in these cages in the bottom right. I could... There's definitely an 8 in the 24 cage. So the 8 is going with 3 cells that add to 16. But I don't think I can actually... There could be a 1 in it. No, sorry, this doesn't look... I think I'm missing something important. What am I missing here? 5. I'm trying to look at places where the symmetry seems to be broken. So I've got lots of 1s, 8s and 9s. I've got this little 5 here. I can't see what it's doing. I mean, yeah, it's pushing 5 into one of those 3 positions, but that doesn't seem to be terribly useful. 4, 8, 9, 3, 4, 5. Can I do better in this row? I've got 3 relatively low digits. Oh, I see. Do I see? Yes, I do see. Oh, that's really clever. Good grief. Right, look at row 2. The key is this square. This square can't be 6 or 7. Because if it is, you can't put that digit in the row. Look, if you make that 7, where do you put that 7 now in row 2? Don't forget it can't be here because that's in the cage with it. So it's not this one, it's not this one, it's not that one. That's also in the box. So this can't be 6 or 7. And if this can't be 6 or 7, I think the only option left for it was 5. Right, that's a 5. Sorry, I should have got that much more quickly. I just didn't see it. So now this little square has to be 2, 3 or 4. That still doesn't create enough. I tell you what we might be able to do, and that's something with this diagonal now, because whatever that is not that, therefore it's that. Yeah, these are different. If we maybe it's better to colour them actually. Let me just do that for you. Just thinking, do I need this to be highlighted anymore? I don't think so. Right, whatever this is, let's make it purple. This is not, we'll make it blue. Therefore this is going to have to be purple again. Therefore this is going to have to be blue. Therefore that's purple. I suppose we just continue that. But the key thing I think is this 35 diagonal. Because now we've definitely got 16 on it. And because these are different, we're adding 13 to that to get 29. Which means these two squares add up to 6. Which means... oh, bother. Well, actually, it's not that bad. It means that's a 2, 3 or a 4. That does give us a 2, 3, 4 triple in both row 1 and box 2. This square's a 6 or a 7, therefore. So this square actually can be blued using the power of colours. Those two squares are 6s and 7s now. Whoa, I want to put 6s and 7s in, not those colours. I don't think we know the colours of these ones though, because we don't seem to have got any information really in columns 7, 8 and 9. But now look what's happening in this box. 2 has definitely got to be in one of those squares, and that 2 sees this square. So we get a 4 and a 2, and a 2 here using the power of our old friend Sudoku. 2 is now locked into the 24 cage, which might be interesting. Oh yeah, no, this is interesting because now I've managed to lock 2 and 8 into it, adding up to 10. I've got 2 more digits to find that have to add up to 14, not using 8. So that they must be 5 and 9. So this cage now is definitely 2, 5, 8, 9, which means... Oh, it means, right, it means we can place 1 in row 6. That's got to go there. So 1 is now in the 18 cage down at the bottom. This is a 3, 4 pair. No. Blue. Where does blue go in box 5? It's got to go there, look. Just using Sudoku and colouring. So, has this made a difference? Have we learnt enough from this that we can do more trickery? I got rid of a 2 from that. That's on the 35 diagonal. So this can no longer be a 4 now. Oh, there's a 4 here. Why don't you do the simple things first, Simon? So this is 2, 3. That's not 2. That's not 8 either, look. So this has become 5 or 9. So this is this could be double 3, couldn't it? Yeah, okay. So this is double 3 or 4, 2. But we don't seem to have. It feels like there's something else now that we're going to have to find. This 8 cage maybe. So it's not 2, 6. Oh, that's no good. I was about to add 8 up and claim that 3, 4 was somehow important here, but it's not. This is not 2, 6, so it's either 1, 7, which would have to be this way round, or it's 3, 5, which would have to be that way round. Now, can we do anything with that? No, I can see 1 in box 6 is in one of 2 places. Wow, okay. 3 in box 8 is in one of 2 places. Twos, threes, fours, fives. No, I'm stuck. This is never a good thing to happen. Now, in this quadruple, look, the 2 and the 5 are definitely in those 3 squares, so we can remove the 2 from this square, which doesn't do anything for us. So close to doing something for us, but it doesn't. I've now got a 3, 4 pair in this column though. Maybe column 1 is where we should look, because those squares are quite restricted. I've not put blue in, so blue is in one of those squares. Don't know which one. Purple is in one of those squares. Don't know which one. But the other digit we've not put in is 2. So 2 is in one of those 2 squares. So if this was 2, these 2 squares would add up to 11, which would mean this would have to be a 7, which it can be. That's annoying. Oh, okay. So purple is in one of those 2 squares. Oh dear, sorry, I think I'm making a Horlicks of this. What have we not used? Is there something that we can do that's going to help us? That's the question. 4 is locked onto this arrow. Oh, that's it. Right, that's all we had to do, is just notice that this arrow's got a 4 on it, because I know it's got a 3 on it, because it can't be a 4, 5 arrow. So that's nice, because that means I can remove 5 from here. I've now got a 3, 4 pair in this row. I can remove 3 and 4 from there. I get a 2, a 3, and a 5, and we're away again, I think. This arrow adds up to 8. That gets me a digit. That gets me another digit. Removes a 9 from this square, an 8 from this square. Now those 2 squares have got to be a 2, 5 combination. So this square is not 2, and we can place the 2 in box 1. This 3 is now useful. 4 and 3 go into the grid. That's useful. Mavericks on the move again. 4 and 3 into these squares. 3 is removing itself from that square now, which means this is a 3 and this is an 8. Good grief. And that's become a 9. Now this diagonal now, we've got those 2 squares have got to add up to 9. Okay. Well, I'm not sure that I can do that. 5 has got to be in one of those 2 squares. Ah, that's useful. 5's got to be in one of those 2 squares, so I can't put it here, because this would have to be a 4, and there's already a 4 in the box. So that becomes 5, which is definitely not purple. This has now become a purple square, which means that square has got to be either 2 or 3, and it can't be 3. So this is 2, and it's not blue. This is 7, and therefore we know purple. Purple is 7, blue is 6, and that must be important. Probably. Probably. I'm not sure. This column, we need to place 2, 7, and 9. That's a 7. So this is a 2, 9 pair. Actually, we can do that using the power of this 2 here. 9 is being locked into something. Oh, 9 is being locked into the 23 cage, actually. Still don't think we quite know what it's got in it. This square is a 7 or a 9. So if these are 5, 7, and 9, these squares at the bottom must be 1, 4, and 8, and that's useful because that means that square's an 8 by the power of Sudoku. This is a 1, 4 pair. Now these add up to 13. I think that says 18, so that must be a 5 to make the cage add up. That gets me the 5 and the 2. Removes the 2 from this cell. 8 lives in the 15 cage now. So we need 7 more that's not 2, 5. Oh, lovely. Look, 3s and 4s. So these 3s and 4s on the arrows come back, and because we can't put a 3 and a 4 in the 15 cage, it must be 8, 1, 6. And oh, that's gorgeous. And so the 1s now do double duty, rule the 1s out of there. This is a 1, this is an 8, this must be a 6. That gets the 6 and the 3. This square's going to have to be something, a 5, I think. Yeah, that looks right. That 1 is fixing the 1 and the 4. So we should be able to write these digits in, shouldn't we? If I could scan, I could do it quickly, but unfortunately scanning is never my strongest point. So we get those digits. Those 2 down there are 4 and 9, which this 4 is quite useful for. 4s and 9s go in the grid. We need an... oh. No, this square can't be 8, 9, or 2, so that becomes a naked single. That's a 5. Therefore, that's an 8, that's a 9, and that's a 2, apparently. That 9 gives us the 7 and the 5. Now we've got the 3 to make the arrow work. That pitches back in there and does work. We've got 1s and 7s to place. And those squares should be 4, 6, and 9. So we should just be able to fill these in if we're careful, like so. Click, tick. Yay. That's a very, very nice puzzle. I got a bit stuck, actually. I'm looking at the time, 33 minutes, so it's definitely not one of the longest solves we've had recently. But for some reason, what was it I missed? This 4 doing some work over here, and also this cell was very clever and what it did in row 2. But there's so much going on in these puzzles nowadays, isn't there? So to break into that, I had to be familiar with Ard's little set trick. And if you didn't know that, it's probably very hard to start this puzzle. But that worked very elegantly. I did like the way we have sort of the dice 5 here. You know, the spots of a dice 5 in these positions, having a relationship to that square. And what's really cute is that you can rule 1 out of this because of these symmetrical arrows. That's very, very nice, and the way they operate with the 15 cage. There's so many little ideas in this puzzle that are just gorgeous. Let me know how you got on. I always read the comments and I enjoy them, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.